Good morning, ladies and gentlemen. Thank you for being here, and thanks for the organizers for setting up such a great event. So I'm going to talk about privacy requirements and technical challenges for storing genomic data. And what I'm trying to advocate is that genomics is bringing probably the most compelling challenge to PLLS. And I'm going to explain you why. This is done work with a number of people, both on the biomed side and on the CS side. So I will assume that most of you know relatively little in genetics, and tell me if that is a wrong assumption, please. Okay, so as you know, this you might know, that genetics is evolving even faster than computer science. In computer science, we like to glorify ourselves about the fact that Moore's law is the most let's say, fastest evolving technology throughout all disciplines. This is not true. If you compare the evolution of Moore's law with respect to what is happening in terms of availability of genome sequencing, you see genome sequencing actually beats Moore's law hands down, and has moved, so sequencing a genome, so DNA, has moved from the cost of something that was in the hundreds of millions to something that is nowadays in the order of 1,000 euros, for example. So it's the same ballpark as a conventional medical examination. So this has been well understood by a certain number of governments. So UK was the first to shoot, and so the Prime Minister Cameron, before making other decisions we have heard about, said, okay, UK should lead the way, and so 100K citizens are going to be sequenced, and of course the US had to wake up at that point, and so there is this 1 million willingness to sequence 1 million US citizens or residents, and we're still waiting for China to tell us that there are going to be 10 million in their case, of course. Now, this is more on the, let's say, political level, but on the side of the industry, especially the IT industry, a lot is happening as well. So Google is offering a service so that you can store your genome at Google for a bargain price of, I think, $25 per year. IBM has also research activities, Microsoft, Apple, Amazon, I mean, they're all there. And many others. So much so that the need was perceived of setting the so-called GA4GH, Global Alliance for Genomics and Health, that aims at defining the best practices in this field, and notably, among others, is working on defining the security and privacy infrastructure that is going to be used in this area. And we are actually working with these people. It's essentially voluntary work, somewhat similar to what is known is in other fields, including, for example, the IETF. So this is what is happening, I mean, very briefly in that area. One dimension we have to be fully aware of is the risks. The fact that, unfortunately, medical data are targeted by criminals and by cyber attackers. So this is most prominent of all the data breaches that have happened so far. Anthem is one of the US largest health insurers, and in February 2015, it revealed that it had been victim of a hack that essentially compromised the data of anywhere between 60 and 80 million people. And so plenty of sensitive data were stolen at that occasion. But this is, let's say, only the tip of the iceberg, and this kind of attacks and mishaps happen again and again and again, so much so that in push towards transparency, the US government has set up the so-called US Healthcare Wall of Shame. So this is a very official website run by the US government in which the companies that are affected by a breach that involves more than 500 people, those companies have to report it. And so if you go to their website, you can see what all these breaches, and you see which company was affected. So it's typically healthcare institutions, or like a large hospital. It can also be an insurance company, the state where it happened, the nature of the activity, the number of affected individuals, the breach, the date at which the breach was submitted, the type of the breach, and so on. And so companies have an incentive to reveal that, because if they do reveal it, then the sanctions against them are capped to a certain level. If they fail to reveal it, then they can be castigated even more severely. We don't have such transparency in Switzerland. Switzerland is not the champion of transparency, as we know. But there is a trend, at least in the EU, to have similar things. Maybe not to the level of making it public, but at least to have a kind of mechanism that would incentivize the revelation of the breaches. And so the new legislation is pushing in this direction. Okay, this is the US. You might say, okay, the US, they are a bit different from us. But if you look, even in the case of Germany, there were cases of a slightly different nature here. This is ransomware. Wenn Cyberkriminelle ein Krankenhaus lahmlegen, which means essentially when cybercriminals essentially stop a Krankenhaus or a clinic to operate by doing ransomware, which is essentially sending a kind of Trojan horse that will go around the network and will start encrypting all the files. And then the criminals would get in touch with the hospital and say, look, if you want us to provide you with the key to decipher that and have your data back, you have to pay us so much money. Usually in Bitcoin. So if you wonder what Bitcoins are for, okay, here's the response. Right? So this is what is happening, and unfortunately it is something that is becoming more and more widespread. So there was a study, by the way, by IBM that showed that this was over the first 10 months of 2015, looking at what is targeted by cyber criminals, and it appears that healthcare is roughly 1/3 of the victims. So this confirms the fact that there is a lot happening in this front, and that it is not there is not enough attention devoted to this dimension. Now, if we come back to genomic data, so why should we protect genomic data? The reason is, well, first of all, it's part of the medical data, and if you believe in the Hippocratic Oath, then it should be protected. But there are specific reasons. Is that the genome carries information about a person's genetic condition and predispositions to specific diseases. So it's a way, the knowledge of the genome makes it easier to forecast the evolution of the health of a given person, right? Which can lead, of course, to genetic discrimination in terms of recruitment, in terms of mortgage and other issues. It also carries information about family members, and genomic data is non-revocable. There's a famous story with Henrietta Lacks. It is known by everyone in the biomed community. There's a nice book about it. I would encourage you to read it if you have the time for that. Anonymization is ineffective because the genomic data are by themselves identifying the people. Right? So my feeling is that genome privacy and security is a grand challenge for mankind, because the required duration of protection goes beyond 1 century, not only because life expectancy is increasing, but also because some of us have offspring, right? And of course, we pass part of our genetic material to the kids. The data size is quite substantial. We're talking about 0.5 terabyte per person if you take all the data into account. And sometimes for medical research, one has to carry out computations on millions, if not more, patient records. And yet, the data are still noisy because the sequencers make mistakes. And so you cannot fully rely on the data as they are. In addition to this, there are correlations within a single genome. So the fact of having a given variant, a given position, means that it has an influence on the probability of having a variant in another position. This is what the geneticists call the linkage disequilibrium. They have a very, very funny and somewhat intimidating vocabulary, I must say. And of course, across genomes, in terms of kinship, the people of the same family, or within the same ethnic group. And so we have to cope with a zoo of semi-trusted stakeholders, which are the sequencing facilities, including the direct-to-consumer companies, such as 23andMe, hospitals, which are also semi-trusted, genetic analysis labs, private doctors, etc. Right? And there is a diversity of applications, and as a consequence of requirements, because this can be used and should be used in healthcare, but also in medical research, and in forensics by police, of course. It has been used for decades very successfully, and in the case of ancestry. Right? So this has been popularized by a movie, Gattaca, that came out a long time ago, 1997. Can those of you who have watched this movie raise their hand proudly? Okay, this is 1/3 of the audience. That's not enough. So I would encourage all of you to watch this movie. It came relatively early, but it tried to anticipate what would happen to society as soon as genetics would become widespread by the fact that sequencing would become so easy to achieve. Right? The movie is good, but I think, unfortunately, it conveyed one misconception, which is a canonical misconception about this field, which is the following, which is genome privacy is hopeless because all of us leave biological traces, cells, such as hair, skin, droplets of saliva, etc., wherever you go. And those cells can be collected and used for DNA sequencing, which is exactly what the police does, right, for forensics. And hence, trying to secure genomes is a lost battle, right? Now, the question to you is, what is wrong with this reasoning? Any guess?
Scaling of the attack.
Yes, exactly, right? So collecting human biological samples and sequencing them is expensive, illegal, prone to mistakes, and non-scalable, right? Even if sequencing techniques keep improving. So high-value attacks, targets such as President Obama has 10,000 people to protect him, and a few of them actually are in charge of doing exactly this. So cleaning, removing the hair, removing the saliva, etc., to make sure that he doesn't get sequenced unbeknownst to him, right? But not everyone, of course, has 10,000 people to protect them. And so essentially the response is indeed that the scalability of the attack is not there. So it will be much easier for cyber. Now, in addition to this, the medical community, both research and healthcare, should not, must not, in any case, should not be the indirect accomplice of massive leaks of sensitive data, because this will, of course, tremendously harm the credibility of that profession. Okay, here I have to mention one slide about, just to make the rest fully understandable, on this genetics in one slide. Okay, so each of us have DNA, as you know, and the DNA is present in all our cells. The same sequence replicated billions of times in each of us, right? And so, which means that actually we are digital. We look analog, but we are digital. Right? And then most of the genome of all the people in this room is almost exactly the same, except for, so the total length is around 3 billion base pairs, so pairs of characters of this kind. It's just a few million places where there are variations, which lets us have different color eyes, eye colors, and height, and etc. Right, and also predisposition to some diseases. So the most common variation is the so-called single nucleotide polymorphism, yet another nice word of genetics, and which is abbreviated SNP and pronounced SNP. Right. So SNP is when there is a difference between essentially the place where differences can occur. And so at a given place, there's a total, as you know, of 4 possible values that correspond to 4 different values, let's say to different chemical components, the names of full name of which don't matter. Let's call them A, C, G, and T. And so if there can be a variation, this is called a SNP, right? And the different possible values that it can take are called the alleles. So the alleles are just a possible various values that can be taken. Usually it's two possible values that are designated as major allele, the one that happens the most frequently, and minor allele, the one that happens the least frequently. And so as there are two positions, it can be either homozygous minor, which is M, let's say small m, or heterozygous, small m, capital M, or vice versa, and a homozygous major. So in this case, we say here, this individual, individual A has combinations A and T, which is major minor, so which would mean it is heterozygous, whereas individual B has a TT, which is minor minor, which is homozygous minor, right? And so on, right? So now, okay, in the case, so of course, in the case of procreation, this plays a crucial role. So here is just on one slide, let's say, user's guide for computer scientists on how to make babies, just in case you would wonder. So it's a two-phase protocol, right? The first phase is offline. So each of the two, Alice and Bob, generate a nonce, right? And the nonce is a semi-random combination based on their own genome, right? So let's start with Bob. So Bob is going to pick randomly a subset of his own genome. So as you see from the first, the upper part and lower part, and this is going to be his own nonce, right? It's called a gamete. In the male case, it's a spermatozoon, and it has many of those. And Alice essentially does the same thing, same process, and generates her own nonce. So this is an offline part of the protocol, right? Then comes in certain conditions of temperature and pressure, the online part happens, which means the two nonces get combined, right? And voilà, this is, voilà, they get combined, and tac. That's the process, right? Which means that 50% of the genome of any of us is coming from our mother, and the rest from our father. There's no way to cheat with that. Right? That's, let's say, fundamental biology. Which means that there is extremely strong correlation of the data of this data within a given family, for obvious reasons. Right? Now, the community, the genetic community, has started to put the genetic data online in order to be for this data to be used by the researchers. However, because of all these correlations and the richness of the data, the issue, the problem is that a certain number of attacks have been perpetrated, and as a consequence, genetic data had to be withdrawn from the internet and protected by, appropriate access control mechanisms. And so there is a huge controversy in this field to what extent one should, so essentially it's a trade-off between facilitating medical research on one hand and protecting privacy on the other hand, right? Voilà. And so there's a long history about this topic. Okay, it would be too much time to go through all that stuff, but let me just provide you with one example, which that refers back to the GA4GH beacon, GA4GH, let's say, organization that has set up the so-called Beacon project. In this project, there are databases where there are actually genetic data that are stored. And so a given researcher can ask, do you have, so this might be a researcher who is in London and asks a beacon that is in, say, Tokyo, do you have someone who has a variation at that place, of that kind? Okay, and the response is going to be yes or no, and so on, right? Because for some rare diseases, it is important it's not easy to find enough people, and so it's important to have access to a large number of databases as opposed to work only with the local database of the hospital, right? So now what some researchers have shown is that, and which is unsurprising for us computer scientists, is that if someone knows the genome of a given individual, by making enough queries, it will know whether that individual is present in the database or not. And the fact of knowing that can be extremely undesirable, because maybe this is a database that contains all the people who have that specific, embarrassing, or very severe disease. They might be HIV infected, or have this kind of cancer, or they have dementia, or whatever, right? So this is extremely sensitive. And so this paper here was published in November in the American Journal of Human Genetics, and we are currently working with the GO4GH to find countermeasures against this kind of problem. It's not easy, because you want to let it be possible to keep doing research in this field, and yet you want to avoid possible embarrassment. All right. Now, just to further emphasize the importance of the field, so medical use of genetics is essentially two things. So first is to facilitate early diagnosis of serious diseases, and the second one is pharmacogenomics, which paves the way to personalized medicine. And the reason here is that, as you probably will know, we do not react the same way to the same medication. Right? So especially for cancer, medication has to be adapted to a given, even if it's the same cancer, the medication will will vary from person to person. And this is going to depend notably on the genomic profile. So this was exemplified by the story of Angelina Jolie. So you know the story that based on her sequencing, she realized that she was at high risk of having a breast or ovarian cancer, and made the decision to have all of them removed surgically, which is of course a very heavy decision. And so this is a major concern for the medical community. What is going to happen now if people show up and say, I want this part or that part to be removed, just in order to reduce my risk of cancer, right? So we have worked on this topic and worked on a system called OpenSnip. So OpenSnip.org is a website you can take a look at. It's quite amazing. It's a website where any of us can upload their own genome if they want, either under a real identity or under a pseudonym. And so we went to this guy who was just one example of the people you see there. So he got his data from 23andMe, so he was sequenced by 23andMe, and he uploaded his own genomic file under a pseudonym. However, he also has a Facebook account under his real name, and it is the same photograph, so it's relatively easy then to match the two. And on his Facebook account, he also has his own family, right? And so based on this, also is a family, and so based on this, it's relatively easy to set up an attack that is going to go against, that will be essentially trying to retrieve and infer data about the genomic data of the relatives who maybe don't even know what genomics is, don't know that this fellow is on OpenSnip, and are not willing to be, to be involved in this kind of thing. So one thing that we have done in this framework is try to anticipate what is going to happen at the Christmas dinner discussions in the future in family, right? Families get together, and so instead of talking about soccer, they're going to talk about something which is way more interesting, which is how much the family is going to be revealed about its own genome to the rest of the world, right? Because some of the members, so here are the different members, right, with their real sequence, and some of them might be willing to reveal a lot, and some others say, no way, I don't want to. And so they have to find a compromise, right, because they don't want a dispute. So they want to compromise, and so for example, this fellow, X2, is willing to unveil nothing, so unveils nothing. X1 is willing to unveil everything, but as a matter of compromise, will unveil only a subset, and same thing for Xn, right? These are the M loci, the places where the variants are happening. And then one can take, so this would happen through the so-called GPPM, Genome Privacy Protection Mechanism, by which they would be able to determine which of the subset they are going to reveal, right? And then one should mimic the behavior of an adversary that relies on common knowledge on genetics, you know, the various statistical data, etc., and the knowledge of the family, in order to realize and perpetrate a reconstruction attack by inference, and from this quantify the genome privacy, from this quantify the health privacy, because this is what matters, and then maybe loop back and say, okay, based on what we observe here, let's fine-tune this device. Okay. As you can see, this can lead to way more vivid discussion than soccer. Right. So based on this, we made some experiments with a family from Utah, for which all the genomes are online. And so, you know, there are 4 grandparents, and then the dad, well, Bob, Alice, and their 5 kids. And this shows essentially how the privacy level declines as soon as you start revealing the data of the relatives themselves, right? If you reveal the data of the unrelated relatives, of course, the privacy level remains high, and then it starts decaying. Here are the 3 scales depending on how you define privacy. It doesn't matter. It's just to show the global allure of the whole thing. Now, coming back to LPPM, just to give you, let's say, an idea of the kind of challenges in this field. One thing that we have tried to do is to think long-term, right? How is it possible to protect this data for decades, knowing that all the crypto will be broken in the meantime, right? And you know, there's going to be quantum computers, blah, blah, blah. So the only way seems to be that, I mean, the conclusion seems to be that it cannot be protected by things based on complexity. So one has to go to something that is more information theoretic. And the only way would be to confuse the adversary. So confusing the adversary is relying typically on honey encryption. As you know, in honey encryption, just in 2 words, the idea is that if there is in conventional encryption, you make use of the correct password, you get the correct you get what you would expect. You get, for example, a gene Q, for example. If you put the wrong password, you get nonsense, or you get wrong password as a message. So the fact of entering a wrong password already gives you, as an attacker, an information which is, okay, this password was not the correct one. So it already leaks some information. In the case of honey encryption, the correct password leads to the correct information. The wrong password provides wrong information, but information that is plausible. In such a way, the attacker does not know whether it is correct or not. How much time do I still have? Where is our chairman? We will start maybe 5 minutes later. So let me try to finish in. Okay. So now, the honey encryption requires this to. I mean, you need essentially to map, for example, if to map things in such a way that they become equiprobable, because maybe these 2 outcomes don't have the same level of probability. The first thing you do, you just make them equiprobable, right? Let me explain this directly on the example itself. So for example, if we want to, so this mechanism is called distribution transforming encoder, and this slide has to be read from right to left. So for example, if gene S is twice more probable than gene Q and gene R, then it should be mapped in twice as many codes, right? As simple as that. So the same reasoning would operate in this case. So in order to generate fake genomes, one just takes into account the basics, well-known statistic distributions of how genomes are nowadays, in order to make these fake genomes credible in their statistical distribution. And so this is essentially leveraging on the process that is similar to arithmetic coding for those of you who are well-versed in that area of technique. I think I'm going to skip the details, but it is essentially creating genomes that are credible as such. Right? And this we published actually last year at Auckland, and it got us my student Chichong the best student paper award, which was good. Okay, so one can show that it is possible to attain a level of precision with enough bits that will make the whole thing as credible as it is needed. And we've also worked, and other researchers as well have worked on a variety of other solutions, including solutions based on morphic encryption, lattice-based encryption, and then, as mentioned, we've worked on these beacon attacks. Some other people, including us, have worked on applying differential privacy, which works more or less in this field, and also, of course, making use of trusted hardware, Intel SGX, I mean, name it. It's an area of very vivid research. There were already 2 DAX tool events on this topic. There was, this is also probably even more important, there was something organized by the School of Medicine. So people who are the potential customers of these techniques organized a workshop in March. All the videos are online. You may want to check that one. And there is going to be in October in Vienna. We should all be in Vienna, right? In October at CCS, a tutorial on this topic as well. There is a workshop devoted to this thing with a call for papers. And the next instance is in November. The call for papers is open until the end of, is until mid-August, so we are still on time to submit your paper. And there is also a competition on genome protection that is going to be presented also in Chicago. So why Chicago? This is going to be co-located with AMIA, which is the American Medical Information Association. Okay. And there is a website, in case you are interested in this topic, called genomeprivacy.org, where you find all the papers already submitted in this field by all the researchers worldwide, the list of the major media news, the tutorials, and the like, and the list of research groups working in this space. There is there's a magazine also in which Stefan Katzenbeißer here from DAX Tool is involved, with a due date by November the 1st, so you still have the time to start research in this field and publish and submit a paper here. Well, and so let me conclude. So PLLS is about protection of long-lived systems. Each of us is actually, or at least hopes to be, a long-lived system. So depending on whom you talk to, 90 years seems to be like a good target, right? But thanks to offspring, the human genome is an even longer-lived system, right? We are talking about millennia here. And more globally, what is happening is that medicine is getting massively digitized, right, by genome sequencing, but also by other topics that I have not addressed, such as electronic health records, emergence of P4 medicine, precision, personalized, predictive, participatory medicine. And so, and I believe that medical confidentiality is nowadays in tremendous jeopardy. So the protection of medical data is a battle we cannot lose, because this is the most intimate data, right? I'm going to talk if you want more on this, I'm going to talk on the WiseJack keynote on Wednesday, and here you find our contributions. And with this, I thank you for your patience and kind attention.